Well, we've started another round of balancing equations, and so now let's look at the kind of equations that are really making people go and panic all over the place as if their heads have been cut off and they're running all over the farmyard in panic. So we'll look at the hardest of these balancing equations that you're likely to get in a test in honours chemistry, and that would be combustion of alkanes. So firstly, let's look at what alkanes are. They're the simplest of the hydrocarbons, and the simplest of the hydrocarbons is methane or methane. And methane, as we know, because of reasons of electron configuration, well, it's made of carbon, and carbon produces 4 covalent bonds. Hydrogen forms 1 covalent bond, and so they all fit together rather nicely like this. And this methane has a formula of CH4. 1, 2, 3, 4. Oh yeah. The next most complex, well, it's still not very complex. It's ethane. Ethane has the first very short carbon chain. So 2 carbon chains joined together, and that will be a C2. And then carbon continues to form 4 bonds. There it is. And this carbon forms 4 bonds, and attached to those will, of course, be the hydrogen atoms that will form 1 covalent bond and fit beautifully there. And so that's C2 and 1, 2, 3, 4, 5, 6. H. And we go on. The next one is propane, camping stove gas. And that has 3 carbon atoms in its chain and, of course, a whole bunch of hydrogen atoms filling up the spare bond that enable each carbon atom to make its 4 covalent bonds. And this will be C3H 1, 2, 3, 4, 5, 6, 7, 8, which is rather nice. So when we look at these, we notice that they follow a pattern. Whenever you look at one of these, you go C, and it's going to be N because there's going to be a number of carbon atoms. And then when we look at how many hydrogen atoms there are, there's an N because there's 3 of them attached below. There's an N, so there's 3 of them attached above. So when we're looking at hydrogen and the number of hydrogen atoms, it's 2N. But there's also these 2 attached on either end. And so it's always 2N plus 2. So that's how we work it out. So if we get C, I don't know, 27, for example, the H's are going to be 27 times 2, 54, plus 2, 56. You can do that with any length of these hydrocarbon atoms, these alkanes molecules, because they get absolutely enormous. So let's have a look how to burn these things with oxygen, because burning is always fun. So let's try something like C5H4, and what's it going to be? 5 2s are 10, plus 2 is 12. So this will be pentane, because it's got 5 carbons, and that's what pent means. And when we're burning it, well, combustion is always a reaction with oxygen, and combustion of these molecules here always produces, you guessed it, carbon dioxide and water. So let's have a look how to balance this. And it's like remarkably easy, even though at first it might not look it. So you look at how many carbons are there on the left side, the reactant side of the arrow. There's 5. How many carbons on the right? 5. So we're halfway there already. Then we look at how many hydrogen atoms on the left side, and there are 12 of them. On the right, water. There's no other place where there's H2, so they have to go there. So 12 hydrogen atoms, 2 hydrogen atoms per water molecule, it has to be 6. 6 times 2 is 12. And then we've got what to do with the waters. So we want how many water molecules. We could calculate it in the number of water atoms. We could calculate it with the number of water molecules. Doesn't matter. Works out the same anyway. So let's look at water molecules because we've got a water molecule here. So here in CO2, there's 5 O2s. Yay! Here in water, there's O, there's 6 O's, so that makes 3 O2s. So 5 plus 3 is 8. We've done it. We've balanced that rather difficult looking equation. Let's make it even harder. Let's go completely mad and invent some ridiculous kind of gigantic alkane, some huge hydrocarbon, and try to balance that. So let's have a look at, I don't know, 31. There's a fairly ridiculous sort of number. Then we work out how many hydrogen atoms are in this if it's an alkane. So it's 2 times 31, 62, plus 2. And that's our, I don't know the name of it, very large alkane. But then we add water, we do some kind of reaction, we produce a certain amount of carbon dioxide and a certain amount of water, and we work out exactly how much that is. So 31 carbon atoms, 31 carbon atoms, 64 hydrogen atoms, 64 divided by 2, work out how many O2s, there's 31 O2s here, and there's 32 oxygens, so 32 divided by 2 is 16 O2. So that makes 47 O2. This will probably be the only time you put 47 as a coefficient in a balanced equation in honours chemistry. Maybe that will last you into AP chemistry also. So these, you'll notice I've done odd numbers of carbons. Because when you do an even number of carbons, you have to add another layer of complexity, another step. And let's have a look at why. So let's just go the next one up from pentane, which of course is hexane. 6 carbons, 6 times 2 is 12, plus 2 is 14. So here's your hexane. The hexane is your basis of gasoline that you put into your car and will burn when you add oxygen and a spark to it, and then it explodes rapidly to force the piston out and therefore turn the crankshaft and make your wheels turn through a complicated series of gears. Combustion with oxygen, it produces the usual suspects. And let's have a look what it does. So, C6, 6 carbons, 6 carbon dioxides, 14 hydrogens, 14, so it's got 7 here. Now let's work out how many oxygens, and 6 O2 here, and 7 oxygens. So we've only got 7 oxygen atoms, so that's like 3.5 O2s, which I don't like. I don't like 3.5 O2s at all. I want a whole number. And so what I do, and it's really very simple, I don't want 3.5. I want the easiest way of getting a whole number. I want 7. In order to get 7 O2s, I need 7 times 2 oxygens. I get 14. Just like in any algebraic equation, if I multiply the left side by 2, I've got to multiply all the other terms by 2 to make it true. I don't know this one yet, so we can't multiply it by 2 yet. So let's have a look at this one. That out, and let's have a look at what we've got going on here. So, 2 C6s, that's 12 carbons. What on earth was I doing there? 12 carbons. And let's have a look now. H14, we've got 2 14s, 28 hydrogen atoms, 14 2s, 28 hydrogen atoms. Now let's look at how many oxygen molecules we've got. 12 O2 and 14 oxygens, that means 7 O2. 12 plus 7 is 19. Another rather unusual coefficient in a balanced equation. But there it is, it works. And if we want to go totally loco and work out some enormous and ridiculous substance, such as C50, H 50 times 2 plus 2, H 102. What's an insane sort of compound? But it does exist. Combustion and O2 produce carbon dioxide and water, and let's have a look at balancing this. So, 50 carbon dioxide, 102 hydrogens, divide that by 2 to make your H2, and that's your 151 H2Os. And then we have our issue, and here's our issue. With 51 oxygen atoms, we can't make an even number of water. We can't make an even number of O2. So we're going to multiply everything by 2. 102, 100. How many oxygen molecules we've got? So here we've got 100 O2. Just cross that out, we've got the O2, and then 102 oxygens, so 102 divided by 2 O2s, 51 O2, and we get the beautiful number of 151 O2. Cross all this nonsense out, uncross that out, and we've got a large and impressive looking balanced equation, but it's just exactly the same as doing a simpler one. And that's probably the most difficult kind of balancing of equation that you're going to get in honours chemistry. Good luck.